So thank you very much for the invite to give a talk in this seminar series. I feel quite honored to be able to give a talk here. So what I'm going to be presenting on is my work on predicting the 2015 North Atlantic cold blob, which you can see on in the figures on the right, the SST anomaly from 2015 in the summer. And also I'm going to talk quite a bit about the European heat wave, which happened also in the summer of 2015. And you can see that again to the right on the figure below. So this is work I've done with a lot of people, so mainly Siebren Dreiftout, Joel Hershey, Bob Lusinga, Alex McGann, Dan Copsey, and Adam Blaker, but there's also been a lot of discussions at Blue Action Project meetings and as well with other colleagues at the NLC. So it's quite a collaborative work. So first question is, what happened in 2015? So at the time, 2015 was the warmest year on record, and currently it's only the 4th warmest. And what you can see in the figure is land and ocean temperatures and for 2015, and the shading shows you if they were record warm or record cold. So what you can notice is the temperatures in most of the world were the record warmest in 2015, but what stands out is the subpolar North Atlantic, where you have the record coldest temperatures. So this is kind of what we are looking at in this work. So what happened in 2015? So the top shows this nice schematic from the Jose et al. Made by Orly. So Orly Duché made this figure, and it shows the timeline of what happened leading to this extreme cold blob in 2015. And in the panel below, we have the temperature anomalies from EN4 over the upper 1,000 meters in the cold blob region. So in 2013, there was an intense heat loss due to a dominant East Atlantic pattern, which got sequestered below the mixed layer and then remerged later in towards the end of 2014. And then the winter of 2014-2015, there was a persistent positive NAO stretching over several months, which led to this reduction in heat content. And you see the minimum in the summer of 2015. And since then, there's been, or in like the winter of 2016, we kind of had a normal amount of heat loss. So the cold anomaly persisted. And what also happened in 2015 was this heat wave. So this is a figure from Duché et al. 2016, the one on the left, and it shows the maximum surface air temperature anomalies over land and sea surface temperature anomalies over the ocean. So what we're talking about over the ocean is in this black box here, the cold anomaly. But at the same time, in the summer of 2015, we had this anomalous warm summer over Europe, so shown in this black box. So the figures on the right, the top panel shows the average surface air temperature in that black box. So the anomalous surface air temperature in that black box over the last several years. And what we can see, I highlighted 2015 as the red dot, and that is an anomalously warm summer that year. At the time, it was the 3rd warmest summer on record. So you can see the red dot, and the panel below shows the mean precipitation over that box, and it was also that year was the record driest year. So we see very dry conditions. So yeah, and one thing you might have noticed, I extended this time series up to 2018. You can see the gray dots. So 2018 is quite interesting. So the top 2 figures you might recognize from the title slide and the 2 figures below are the same thing, but for 2018. And you have some very similar patterns, although the temperature anomaly did not go to as deep. It didn't penetrate as deep in the ocean as it did in 2015. But in 2018, you have a similar pattern in the ocean with the cold temperatures and anomalous warm temperatures to the south of that. And again, you get a heat wave or an anomalous warm summer over most of Europe. So the main difference is the Scandinavia in 2015 was colder. So this makes 2015 an interesting year to test prediction systems, seasonal and decadal prediction systems, to see if they can capture these extreme events. So first I'm going to talk about the 2015 Atlantic cold blob, so more the ocean focused one, and this is currently very much work in progress. So it's just a glimpse into what I've started working on over the last over the last while. So one study that came out this year that's very relevant is from Elizabeth Maroon. So what she did is she looked at the NCAR decadal prediction system, so CESM DPLE. So in the figure in the middle, the black line shows the observed temperatures in the cold blob region, and the orange line is the mean from the decadal prediction system with 1 year lead time. And what stands out is it picks up the longer timescale variability quite well. And if you look at the range, the orange shading, most of the variability, the interannual variability, is captured in the model range. But what really stands out, where you see this gray line, is in 2015 you have a lot colder sea surface temperature anomalies, and that isn't captured in the range of the prediction system. So they asked, this paper was very thorough. They asked a lot of questions and tried to answer them. So first of all, was the ensemble too small? So they have 40 ensemble members and they added another 20, and that didn't make a difference. And then they also asked, can the prediction system actually simulate the extreme cold and persistent positive NAO from 2015? And looking at the uninitialized prediction system, they were able to see anomalies this strong, but they were very rare. And from that analysis, they estimated that you would need at least 440 ensemble members to predict this. There's also sea ice balance, sea ice bias. So the Barrett's-Kara Sea has too little sea ice in their model, so they changed the atmospheric initial condition. It improved the sea ice in their prediction, but it didn't improve the SST anomaly. And also the way their prediction system works is they initialize using a forced ocean sea ice run. They use full fields from the forced ocean sea ice run, and those initial conditions are too warm and too salty. So they tried using an observational-based initial condition where they used anomalies from the EN4 data, and it decreased the warming, or it decreased that it's too warm, but it's still warmer than it should be. So what I've done in my work is I'm repeating some of this stuff using HADGEM 3 GC 3.1, and a big difference between the CESM decadal prediction system is we're using higher resolution. So their prediction system is 100 kilometer resolution, whereas we use approximately 25 kilometers in the ocean and 60 kilometers in the atmosphere. Our setup is a bit different. So we use a present day control simulation that's about 300 years long, and we define our climatology as the last 200 years. And then we use anomalous 3D ocean initial conditions. And these anomalies come from different sources. One of them is, so we do the forced ocean sea ice model, so for short, FOSI for short, and we use the JRA atmospheric forcing, and we also try it again with the DFS atmospheric forcing, and we also use anomalous initial conditions from EN4, similar to what was done with the CESM decadal prediction system. All of these runs are initialized on November 1st, 2014, and the atmosphere initial conditions are taken from the present day control simulation. And at the moment, each experiment has 5 ensemble members, and they're all run for 5 years. So here we just look at how do the forced ocean simulations that we initialize from perform. So in these plots, we have the blue curve showing the heat content anomaly over the upper 200 meters from EN4 data, and the orange curve showing the forced ocean model data. And the panel below is the same thing, but for the DFS forced run. So what you can see in the JRA forced run, the advantage is that it goes longer. So this forced simulation was run until the end of 2017, but you notice there's a strong decreasing trend in temperature, or trend in the heat content, which is a lot stronger than observations. On the other hand, the DFS forced run, so the Drakkar forcing set run, follows the EN4 data a lot better, but it ends in 2015. So we looked at what happens in both of these. So if we move on, we look at some of the results. So these orange lines are the same orange lines as in the previous figure, and the black line shows our ensemble mean. So the anomalies from our ensemble mean, and again for upper ocean, the upper 200 meter ocean heat content. And what we see, which is similar to what happened if you take a closer look at the CESM prediction system, we get the cold anomaly weakening, so becoming slightly warmer. But what we do see is when we go out to like 2017, we get a cooling trend, and the cooling goes almost as far as the cooling in the forced ocean simulation. And a similar thing happens with the DFS force simulation, where you get this cooling trend again in the ensemble mean. And then looking at the EN4 initialized data, the interesting thing is in the ensemble mean, it doesn't get warm as quickly as it does for JRA or DFS. And again, you see, although the timing's a bit different, a secondary drop, or you see a drop in temperature later on. And some of the ensemble members get heat content that's almost as low as in the EN4 data. So yeah, so this has just been 5 ensemble members for each experiment. So what can we learn from this? And what's quite interesting is when you start looking at individual ensemble members. So this is an example of an ensemble member from the JRA initialized run. And what you can see in January 2017 is you get this drop in temperature, which brings it almost as cold as the cold blob was in the forced ocean run. And in 2019, you get another drop in temperature. So if you take a look at that a bit closer, you notice we had a persistent positive NAO when this second drop in temperature happened. So you can see this from this is just station-based NAO index from the ensemble. So from this ensemble member, and you see there that we have a positive NAO from November to March. So that's quite interesting. And if you look at other ensemble members, so this is the second one from JRA, you get these reductions in temperature, and they often line up with a persistent NAO. And this is one from DFS, where you see some drops in temperature. And interestingly, if you move on to the EN4 forced runs, this one ensemble member displays a very similar and structured double decrease in the temperatures, like you see in the EN4 data. And this other ensemble member is able to capture the second decrease in temperature, so the one happening in the winter 2014-2015, although it isn't quite as strong as it was in observations. So even though this is still very much a work in progress, there's a lot of interesting things that we can start pulling apart from these experiments. And one thing, although we haven't quantified it yet, that's quite interesting, is that we're noticing there's quite a few persistent positive NAOs happening after it's initialized. So perhaps the timing, our method of prediction doesn't get the timing quite right, but it does make it more likely to have a persistent NAO happening. So this is all still work in progress. So the next thing I'm going to talk about is the 2015 European heat wave. So this has been published in 2019 in environmental research letters. So you can look up the paper if you're interested. So again, here we used a similar model setup where we initialized this time from May 1st, 2015. And we used as our control simulation, or as our climatology simulation, a historical plus RCP 4.5 had GEM3 GC2 simulation. And we defined our climatology from 1981 to 2010. And we did ocean initial conditions as 3D temperature and salinity anomalies taken from a forced NEMO run, which is then added to the climatology from the coupled run. And then our atmosphere initial conditions in this case, they also include sea ice initial conditions. And we use them taken from 3 different time points from the historical plus RCP 4.5 coupled simulation. And the results I show are the difference between the anomalous initialized simulations and the climatology. And these differences always both use the same atmosphere initial condition. And for each experiment, I have 30 ensemble members. So just to show you down here in the figure, we have the SST anomalies for April, May mean in 2015. And this is the initial condition anomaly we took from the forced ocean run. So they look very similar, although in the forced ocean run, since it's not a 2-month, it's instantaneous, you see a lot more small structure. So moving on to the results, on the right we have the temperature anomalies from 2015 from ERA 5 data, and on the left we have our results from our coupled experiment. And surprisingly, we get the warm temperatures over Europe quite well, and we get similar patterns in the surface air temperatures. So just to say, this is June, July, August surface air temperatures, and everywhere where we have the dots or the stippling, that means the data isn't significant at 5%. So this is so this is quite nice, and this is the ensemble mean. So that's quite a good result. And if you remember from earlier, that 2015 was also the driest summer on record. So we looked at precipitation, and our ensemble mean has in similar regions has low precipitation over Europe, which is quite good. So far this is quite good, but this is quite coincidental because we arbitrarily chose the initial conditions for the atmosphere, but they worked really well. So we're going to dig into that a bit more. So first of all, we're going to ask, what was the role of the ocean? So what the results I just showed, what you can see on the right, was using the full global initial condition. And then we tested, because of the cold blob and the relationship between the cold blob and the heat wave, we tested the initial conditions, only initializing them in the North Atlantic region. And we tapered these anomalies. So what we get there is we still get some significant warming over Europe, but it's not as strong as the warming we see when we use the global anomaly. So then we did the inverse experiment, and we noticed again, so we didn't put any anomalies in the North Atlantic, but we had them everywhere else globally. And again, we notice warming conditions over Europe. So if you just add these two anomalies together, you almost get exactly the same pattern you got in 2015. So this suggests that the heat wave in 2015 wasn't only driven by the North Atlantic, there was also influences from further away. So yeah, so now we move on to this arbitrarily chosen initial condition for the atmosphere. So this is the same plot as before, and we labeled this atmosphere A and made it pink. And so this worked quite well. Then we tested two different arbitrary atmosphere initial conditions, which we labeled atmosphere B and atmosphere C. So what you can see in atmosphere B, you get some of the warming, especially over Spain and France, but you don't capture warming over the full European region, whereas in atmosphere C, you get a cold anomaly. And remember, these are coupled, since both the climatology run and the anomalous initialized run are using the same atmosphere initial condition. These are the coupled effects of having that atmosphere initial condition. So it's very dependent on how you initialize the atmosphere. And we could have just got this by chance, and it was a lucky coincidence that our first try worked really well. So we said, how can we determine if it and why it worked really well? So the plot on the bottom left, what I'm showing is the little gray dots are correlations between the SST anomalies and the surface air temperature anomalies at the beginning, so May 1st, 2015. And from ERA 5 data, what you notice is you get, so it's taken, if you look at the year, that's the year of the SST anomalies, and all the dots are for one atmosphere year. So from one surface air temperature year, and I've done pattern correlations between the anomalies. So what you see is every time there's one year that stands out, and that's always the same year as the SST anomaly. So we put a little black triangle. So they are quite similar, the surface air temperature and the SSTs. And when you look here, if you look at 2015, you see that in atmosphere A, which is pink, we get the highest correlation between surface air temperature and SST. And whereas atmosphere B and C don't do so well. So we asked ourselves, was it coincidence that we chose that year from the coupled simulations? And we repeated the same thing, but this time with the initial conditions from the coupled simulation. And we noticed that if we would have chosen the best match with the ocean, we chose the third best one. So this suggests that maybe we can do well predicting extremes if we choose a good analog atmosphere initial condition to the ocean initial condition. So one last thing to talk about is what is the role of the sea ice? Because if you remembered, we put the sea ice in with the atmosphere initial condition. So what these figures show here, the top panel is the sea ice thickness from biomass, and the next three panels are the sea ice thickness from atmosphere initial condition A, B, and C. And what you notice, the patterns between A and observations isn't that similar, but it is the one that has the thinnest sea ice thickness. And to the right of this, what I show is the surface air temperature anomalies over the box over Central Europe. So the pink is atmosphere A, and we know that that gets a warm temperature anomaly. And from previous slides, we know, so the purple is using atmosphere B and the brown is using atmosphere C, and they don't capture this warm anomaly over Europe. So now what we've done is we've kept atmosphere A in the anomaly for the atmosphere initial condition only and changed the sea ice. And as soon as we change the sea ice, we no longer have the warm temperatures over Europe. And then we did vice versa, where we kept the sea ice anomaly and changed the atmosphere anomaly to be A and B. And then again, we lose the warm temperatures over Europe. So this suggests in predicting the extreme summer of 2015, we need to have a good combination of initial conditions between the atmosphere, ocean, and sea ice in order to be able to predict this extreme event. So yeah, so thank you very much for listening. And so my take-home messages are that what happened in 2015, the cold blob in the North Atlantic and the European heat wave make an interesting test for seasonal and decadal prediction systems. And when we're trying to predict the extreme cold temperatures in the North Atlantic in 2015, the subpolar North Atlantic, it's been shown to be very difficult to do this. And in our model setup, we were able to simulate and maintain a negative temperature anomaly, although it does get a bit less negative. And the timing of what happened, this reduction in temperature in 2014-15 was off by a few years. And then moving on to the heat wave, we were able to do a really good prediction or a reforecast of the 2015 heat wave over Europe. However, this could have just been coincidental by the choices we made. But digging into this a bit, we notice that it is very dependent on choosing a best combination of initial conditions where the atmosphere initial conditions, ocean and sea ice initial conditions work well together. And that's it. Thank you very much.